Good afternoon, everybody. Recording in progress. So we have a liftoff. So, okay, first I wanted to address a particular question that was raised yesterday. I don't know if João Pedro is here with us. Is you? I don't know. Is João Pedro here with us? Hey, okay, he's with us. And not only him, but since he was the one that raised the question about the Riemann tensor, so let me try to share. Let me see if I can. Let me see if it's working. I don't know if it's working. I'm trying to share with the other device. Well, I'm completely helpless with Zoom, apparently. Uh, Let me try again. Nope. Well, let me try to do this only with words. Okay, I was gonna show this, but I'm not getting the right. I don't know. I'm an old man confused with technology, apparently. So, okay, the thing is, I think the question that João Pedro raised yesterday was about the Riemann tensor, because in the previous lecture, I presented the Riemann tensor, and we talked about how to get to the Ricci tensor from the Riemann tensor by contracting the first and third indices, right? So João Pedro asked me why the first and third indices. Well, in this convention, right? We used the first and third indices because if you contract, you can try this by hand, and you see that I'm right. If you contract the first and second indices, you're gonna see that it becomes zero because the two leftover indices are symmetric. Okay, so if you contract the first and second indices, and then do the symmetrization of the two leftover indices, you're going to see that it goes to zero. Okay. If you do the contraction of the first and fourth indices, you get the same result as the first and third, only with a different signal. Okay. So if you contract the first and third indices, you get the Ricci tensor. If you contract the first and fourth, you get minus the Ricci tensor, right? So this is the only contraction. First and third indices are the only contraction that does not equal to zero, or I mean, you get the same result otherwise if you contract first and fourth indices, only with a difference in signal. So it's a question of convention most of all. So I think Wald has a different convention about which index of the Riemann tensor is the raised one. So I think maybe the convention of contraction, index contraction, is different there. I don't really remember which indices that it contracts to obtain the Ricci tensor, but this is the thing. So I hope that it clarified a little bit for you, João. If you want to try to do these contractions, different contractions by yourself, you're gonna see what I'm talking about. And if you have any trouble with the computations, you can ask me in a future lecture, and we can do it, or I can try again, try to show here. I don't know why it didn't work. So okay, so let's go to today's lecture. Let me share this. All right. So here we are. Welcome those who survived yesterday. Black hole perturbation theory. So today we're going to really talk about perturbations. Uh, well, I think that I'm getting in the way of the slides. So I'll turn off my camera here. Now we can do it. Okay. Okay, so today first, I want to talk to you about GR in the weak field limit. Okay. Then we're gonna discuss a little bit of what a gauge symmetry means in general relativity. And then we're gonna see how the perturbations work in Minkowski and see what these gravitational waves will look like. Okay. So uh so let's go. GR in the weak field limit. Okay. So the basic assumption in the regime of weak field is that our spacetime is described by this metric eta, which describes the Minkowski metric, as I showed to you guys in the last slide of yesterday's lecture. So Minkowski spacetime is a flat spacetime, okay, without curvature. So we start with a curved spacetime, g mu nu, but this curvature is so small, right? The gravitational field is so small that we can model our spacetime by flat spacetime plus some small perturbation, okay? With the condition that the components of the perturbation are very small compared to the components of the Minkowski spacetime, okay? You may wonder and ask, well, Vitor, but the components of the Minkowski metric are not constant in all coordinate systems. So this condition here is only valid in some coordinate system, and you would be right to assume that and to ask this. But we're gonna see that there are some types of transformations that we can perform, right? Some freedom, some liberty that we can take that will allow us to to maintain, right? To preserve this condition in different coordinate systems, okay? So don't worry about that yet. We're gonna get to that. Okay, so there are two possible interpretations for this equation here. One of them is the first that I already said, that is to say that, okay, we have a flat space-time plus a small perturbation, okay? So we have our manifold, M, and this manifold is being perturbed, okay? Or we can see this as a tensor field, a O2 tensor field, H mu nu, living in Minkowski background. Is very subtle. The difference is very subtle because in both problems, in the two situations, we have different manifolds, okay? Here, the manifold is the manifold from Minkowski space, right? Here is the full manifold, curved manifold, but okay, plus a perturbation, okay? So it's go with this second interpretation, okay? It's a 0-2 field, so we're gonna regard H mu nu as a field, a 0-2 tensor field living in Minkowski, okay? Living in flat space-time. Okay, so what we're gonna do is we're gonna use that definition that I said to you guys that was important for you to remember from the Christoffel symbol. Well, I guess my picture is still in the way of the slides. So let me just stop for one sec here. and start sharing again. I'm sorry, guys. Promise I will get this straight. Okay. No, 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 no. I have to change the type of the layout. Let me share here. Okay, now. Okay. Now we are on our way. Okay. Sorry, guys. So, okay. So we're gonna plug in this equation here into our definition of the Christoffel symbols. So remember from the last lecture that we found a way to describe the Christoffel symbols, the affine connection in terms of the metric, okay? And we're gonna plug in our equation, so G becomes eta plus a perturbation, okay? You're gonna see here that we used that the inverse metric is actually eta minus H. That is because it is the only way that we can maintain the fact that G mu nu contracted with its inverse gives us the delta, the Kronecker delta, okay? So the identity matrix, okay? So this is the representation of the inverse metric in terms of the flat metric and the perturbation, okay? All right, so now we have this, okay? And we gotta distribute these contractions, okay? But the secret here is that we wanna do this in first order only in H, okay? Because this perturbation is so small that terms of second order in H are neglectable, okay? So we're gonna throw out the terms in second order on H so that we can have a first order equation on the perturbation, okay? So we're gonna distribute these contractions here, okay? And what is left is this. Wow. Here we use that all the derivatives with respect to the flat metric are 0, all right? So what is left is this, okay? Here are terms of order H squared. So we're gonna throw this out, right? So our Christoffel symbols can be defined as this, okay? Now, from the previous lecture, we had the Riemann tensor, right? Which we can describe in terms of the Christoffel symbols, which we now know how they looked in our perturbation scenario, okay? So this is the Christoffel symbol in the perturbed scenario. So we're gonna plug in now the Christoffel symbols here and see what this yields in terms of the Riemann tensor, what we call the perturbed Riemann tensor, keeping in mind that we're always, every manipulation that we do in perturbation theory, at least in this kind of perturbation theory, which we are making our way to the linearized Einstein equations. So we're doing this in linear order in H. So we want to throw out every terms of second order or higher, okay? So you see that these terms here, so we have a Christoffel symbol contracted with another Christoffel symbol. But you see clearly here we're gonna produce terms of second order in H, right? If you remember here, if we multiply this with itself, right? We're gonna have derivatives squared of H, okay? So these terms we're gonna throw out, right? Because here we clearly have terms in second order on H. So we're gonna take these derivatives here and subtract them to see what happens. So this two terms is exactly what is left here. And if we put them together, we have this, okay? So we apply this partial derivative here and this partial derivative here. Some terms will cancel, okay, because we used that partial derivatives commute with each other, right? So taking a partial derivative with respect to x and then with respect to y is the same as taking with respect to y first and then to x. So these terms that we produce here will throw out, okay? You can always repeat these computations at home. And if you guys have any questions about them, you can always ask me, no worries. So what is left here is this expression here, okay? So second derivatives, all in terms of second derivatives on the metric, on the perturbation, right? On the metric perturbation, H, all right? So you're gonna see that this lecture and all subsequent lectures, they will not contain a lot of conceptual new things, but a lot of computations and calculations and so on and so forth, okay? All right. So from the Riemann tensor, we obtain the Ricci by the contraction of first and third indices, right? In this convention. So our perturbed Ricci tensor will become R mu nu, and it's just what we did was just do the contraction with between alpha and mu here. So if we did this here, we obtain this expression here, okay? R mu nu is equal to half, and these second order derivatives, the second derivatives of H, and some of them are contracted with the indices here, okay? So here we have this contraction here, and here we define this operator here, okay? All right, and where we use that H is just the trace of the tensor H mu nu, okay? Again, you can always repeat these calculations at home, and any questions that you have about them, you can send to me, and we will deal with them in a future lecture. Okay. So taking the trace of the Ricci, we get to the Riemann scalar, the Ricci scalar. Okay. So we take the trace here, and we end up with this expression here. Okay, so now if you remember from last class, all right, from yesterday's lecture, you remember that to construct the Einstein tensor, G mu nu, we needed the Ricci tensor, the Ricci scalar, and the metric. Now we have all the ingredients to construct the Einstein tensor, and thus to construct the Einstein equations, okay? So from the previous lecture, G mu nu is this tensor here, which we can write as this combination of the Ricci tensor and the Ricci scalar, okay, with the metric, and we plug in the above what the previous the previous equations we obtained, the previous expressions, and what we have left, always maintaining in first order in H, right? So remember, in here, in the Ricci scalar, we had second derivatives, right? Of the metric perturbation, okay? So if we multiply H by R here, clearly we're gonna have terms of order H squared, so we're gonna throw this out, all right? And here is what is left. Open this up, we get to this, all right? I'm gonna develop this some more and see where it leads us, okay? So to simplify this expression here that is quite big, we're going to introduce a new notation. So this is not a coordinate transformation, right? This is not a transformation at all. This is only a new notation. So we're going to introduce the H mu nu bar, right? Which basically it relates to H mu nu, the original H mu nu, like this, okay? So this is what we call the trace reversed perturbation, right? The trace reversed, because if you take the trace of h bar, we see that the trace of h bar is exactly minus h, okay? So we call this the trace reverse perturbation, okay? And if we plug in, so if we come back here and substitute h by this expression here, we're going to see that in neglecting, obviously, neglecting terms of second order and h of h squared, we get to this expression. Okay, so this is what we call the linearized Einstein equation. Okay, so this is the, so now you remember that I said in the yesterday's lecture that one of the problems, one of the things that makes the Einstein equations so difficult to solve is the high nonlinearity of these equations, right? These equations are highly nonlinear, but now we found a way to do this in a linear way. So see, you can see this, if we solve for h, we are basically solving a linear differential equation, right? Second order, okay, but linear still, right? If we set this equal to 0 or equal to some energy momentum tensor, so we're gonna have, we have here a what we call the linearized Einstein tensor, which describes gravity which describes linearized gravity, okay? Gravity in a linearized regime, okay? Okay, so let me pause here and see if there is any questions about our train of thought here, the development of the linearized Einstein tensor. Is there any questions that you have? Let me see, the chat is popping, but I don't know if any questions? No questions. Okay. All right. Well, let me just, okay. All right, so I will proceed. I think I stopped sharing. Oh my God. Can you hear still?
We can hear you. Yeah.
Okay, okay. I thought the internet went down. Oh, book is it's giving me a hard time today. Okay, I'm back. So I'm sorry, guys. My computer is giving me a very hard time today. But okay, so no questions so far. Is so far very intuitive, I think. So we have to talk about some gauge symmetries, what it means what a gauge symmetry means in general relativity, because we will need some help in solving these equations, okay? Because as you can see, these are quite extensive, right? These are quite extensive, even more the original Einstein equations, even though they are linear now. But every help is worthwhile time talking about it. So let's see what we can arrange with some symmetries, okay? So solving the Einstein's equations, what it means for that, it means solving for G mu nu, right? It means solving for the metric components, which means for that it means it means that we need to solve 10 ODEs, okay? We need to solve 10 differential equations, G mu nu, that in a vacuum, right? It won't change the scenario and the degrees of freedom here, but for the Einstein equations in vacuum, we need to solve 10 differential equations, right? Which are these 10 equations, because G is a 4x4 tensor, okay? It's a 4x4 matrix, if you will. But it is symmetric, right? So we have 10 independent components of the tensor, the Einstein tensor, right? So we have 10 independent differential equations to solve for 10 unknown functions, G mu nu, because the same way G is a 0-2 tensor, right? Which can be represented by a matrix, a 4x4 matrix, but this tensor is also symmetric, right? So you have 10 unknown functions, independent unknown functions that we must solve for, so we can have a full solution, okay? All right, well, but some degrees of freedom we can right away remove by some identities, okay? So the Bianchi identity, right, that I showed you guys as a condition, a property of the Riemann tensor, and it implies that the divergence of the Einstein tensor must be equal to 0, okay? So this poses 4 constraints, which means that we lose 4 degrees of freedom here, right? Because this index is contracted with this index here, right? So we have 4 equations that must be solved here. So we have four degrees of freedom less than we had previously, okay? Which gives us a problem instead of solving, instead of helping. It seems to raise a problem here, because now we have less equations than unknown functions, right? So we have an indefinite system here, 10 unknown functions and only 6 equations. But thanks to the principle of general covariance, right, our freedom to make coordinate transformations and not alter our physics at all, we can do some transformation here of the metric tensor, right, of the components of the metric, that helps us lose the 4 degrees of freedom that are left over here, okay, that are spoiling our system, okay? Which means, why we lose 4 degrees of freedom? Well, because we have four components here, 4 coordinates, right, to impose this transformation, right? So we have G mu nu is a function of 4 coordinates. So a coordinate transformation is a set of 4 functions, right? Set of 4 constraints that you input on the system. Okay, so now we have a definite system with 6 unknown functions and 6 equations. So far, so good. Okay, so we have a much more simpler system here. We had 10 and 10, right? 10 equations for 10 unknown functions. Now we have 6 unknown functions and 6 equations. So a lot easier, okay? But something tells me that we could do more. We could ask for more, maybe more symmetries. We could wonder if our system has any leftover symmetry that could help us. Well, let me just pause here and see if okay. Well, I'm worrying about the chat, but I guess I will try not to worry so much about it. If Bruno, if something pops up and I don't see it right away, you can always interrupt me and warn me of some question that is raised. So
Certainly, yeah, don't worry about it. Yeah.
Okay. So moving on. Sometimes you may stumble upon an expression in general relativity textbooks that will say to you that general relativity is an invariant theory under coordinate transformations. And we saw that, right? We constructed our manifold, we constructed our tensors, we constructed every object so far. So we could be that way, right? So we could satisfy the principle of general covariance, okay? So, yes, clearly our theory is invariant coordinate transformations. But you could stumble upon some references that will say to you that this invariance in the coordinate transformation is what makes general relativity invariant under a certain group of diffeomorphisms, right? And you would say, well, as far as I am concerned, coordinate transformations and diffeomorphisms are completely different operations, and you would be very right to do so. But I'm going to show you, at least not in a formal way, like the mathematicians would like, maybe. But we're going to do this rather intuitively to see that there is some correspondence here between an invariance, at least in general relativity, between an invariance under coordinate transformations and an invariance under diffeomorphisms. Okay? So you see we're trying to make an analogy with electromagnetism, right? In electromagnetism, you have the vector, the potential vector, right? And this potential vector has a gauge freedom, right? Because after all, the magnetic field is defined as the rotational, right? Is the cross product of nabla with the potential vector, right? So this would go to zero anyway. So we have some gauge freedom here, right? Due to a vector identity, right? And we want to show you that there is also an analog freedom, which we call gauge freedom. Some people don't like to call this a gauge freedom, but we will call it anyway, because physics is all about abuse of notation and names, right? So, okay, so GR's gauge freedom, sometimes referred to as GR's invariance under diffeomorphisms, right? So you can see that it would be very easy to mistake one for the other, right? Which, right? Which of these expressions is a coordinate transformation, which is a diffeomorphism, right? Here in equation 11, we have a coordinate transformation, okay? What we represent mathematically as a coordinate transformation. So we see that we put the prime on the indices, right? And in here, the prime is on x itself, right? And there's a reason behind it, right? Because coordinate transformations, they relate two or more different set of tuples, set of coordinates of the same point of the manifold. So in a coordinate transformation, we are always talking about the same point of the manifold, but we are taking this point of the manifold to two different copies of Rn, right? And through a function phi, we can relate the coordinates in one copy of Rn with the coordinates in another copy of Rn, right? In a diffeomorphism, we are talking about two different points in the manifold, right? A diffeomorphism maps a point of the manifold into another point of the manifold, okay? We're going to see this more intuitively through this picture here. So this is nowhere near a formal demonstration, right? But I guess it works for the intuition it brings, okay? So if we focus in this half of the picture, so this upper half here, so we see that the point P of M is being taken by the coordinate functions f and g to a point in Rn, okay? And this point x mu and x nu they will have they will have coordinates in this Rn, right? A set of coordinates here through this function f, and this same point P is going to have a different set of coordinates in R prime n, right? Is a different copy of Rn. Through this function G, we have a different function, so we have a different set of coordinates here, okay? And we can relate this set of coordinates through this function phi, okay? This is what we talked about in the previous lecture when we talked about the principle of general covariance and the Einstein equivalence principle, right? So the Einstein equivalence principle is translated geometrically by the fact that locally our space-time is homeomorphic to Rn, okay? And in the principle of general covariance demands that we always have these functions at psi, right? And that so that we can relate different sets of coordinates, right? So that we can translate them if we need it, okay? Okay, so this is a coordinate transformation, right? And now we're going to see what a diffeomorphism does, okay? So we start with a point P, and through a diffeomorphism psi here, we're going to take point P to another point Q, right? On this manifold, all right? So see that we are connecting two different points through this diffeomorphism, right? Okay, but this point Q can also be taken to a certain copy of Rn through some coordinate function. Here we're going to use the coordinate function G. All right, and this diffeomorphism induces a set of real functions, right? This other psi here, so that we can relate these 2 points, right? Okay. So imagine that we, instead of a general diffeomorphism, we applied an infinitesimal diffeomorphism, right? So that these points are very, very similar to each other, but still different through this, but connected through this diffeomorphism, right? Which relates them in a very strong way in mathematics. These points I think that I can say this. I'm not quite sure, but I can say that the neighborhoods mapped through the diffeomorphism can be said to be isomorphic. I will, the inverse is 1 to 1.
Sorry, Victor, I think we lost your...
So let's look at this mapping here. The mapping, okay.
Excuse me, yeah,
sorry.
I think your audio got frozen for a little bit. So can you go back maybe 2 minutes?
Okay, sorry. So can you hear me okay right now?
Now we can, yeah.
Okay. So okay, let me get back a little bit. So as I was saying, so a diffeomorphism will take P to another point Q on the manifold, right? And this point Q can also be mapped to the same copy of Rn by the function G, right? And this diffeomorphism through this coordinate function, which is also 1 to 1, right? Is a homeomorphism. So it's 1 to 1. It has an inverse. It induces a set of real functions that will connect the points x nu prime with x tilde nu prime, right? So x tilde is the point that is the image of point Q through G, and x nu prime is the image of point P through G. okay? So imagine now that we applied an infinitesimal diffeomorphism here. So being a diffeomorphism, these functions psi have all the properties that you would expect from a diffeomorphism, all right? So if you look at this mapping, the mapping of P to this copy of Rn, right? You can see that due to the nature of functions psi and g and little psi, small psi here, these mappings are completely equivalent, right? So map P to X nu prime here. We can take this path here through G, or we can take this path here, first through psi to Q, right? G acting on psi of P gives us X tilde nu prime, right? And by using the inverse function, so psi to the -1 here, we'll get back to X nu prime, right? So I hope that you can see this, right? This mapping here is completely equivalent to this mapping here due to the character of these functions, right? They are homeomorphisms and diffeomorphisms. So this mapping here is completely equivalent. To say that they are equal, I think is a very strong statement, but I didn't know otherwise how to put this. But this is only an intuition, it's not a formal, not a formal demonstration of any sort. But this is why, in general relativity, the invariance under coordinate transformation is equivalent to an invariance through diffeomorphisms here, because diffeomorphisms in this context, so this action, this character, this performance of diffeomorphisms here are very much alike a coordinate transformation, right? Wald calls this way of looking at diffeomorphism general relativity in his book as a passive viewpoint on diffeomorphisms. If you want to check the more mathematical proof of these relations, you can go to Wald. He does a very formal demonstration on this on this equivalence, right? So as I stated previously, right? This is known as a passive viewpoint of diffeomorphisms, right? Let me pause and see if there are any questions regarding this demonstration of this not very formal, this very intuitive kind of demonstration that we just did. Is there any questions about it?
Feel free to unmute yourself if you want to ask anything.
Well, okay, then we can always get back to it at some point. But if you got confused, I can explain it again. It's not a problem, okay? But it's very important that we all see this, right? Because we're gonna use it. We're gonna use this in our favor. So if you don't see it yet, you have to believe me and trust me on this, okay? If you're not convinced, maybe you're not convinced. It took me a while to be convinced of this. You can always, as I said previously, you can see a more formal passage on this on Wald, okay? But we're going to use this in our favor because under infinitesimal diffeomorphisms, the metric tensor and thus the metric perturbation will transform like this, right? We can always represent infinitesimal diffeomorphisms as transformations generated by a vector, right? So if we change our coordinates x alpha to a x alpha plus C of alpha, C sub alpha, okay? We're going to expand this, right? This is the Lie derivative of the metric, okay, with respect to psi, okay? Xi, I don't really know how to pronounce this the correct way, but I guess, yeah. So we're gonna do this, we're gonna open this up, right, with the definition. If you have seen it, if you have encountered, if you have some experience with the Lie derivative, but if you don't, you're gonna have to trust me on this also. But we can also we can always demonstrate this later if we have some time left. But okay, so this is the way that our metric perturbation will transform under an infinitesimal diffeomorphism, which means that this metric perturbation H prime is completely analogous to this one in the sense that the physics that this represents is exactly the same physics that this perturbation represents. So as far as physics is concerned, this perturbation and this perturbation are the same, right? Due to the fact that our theory can be said to be invariant under diffeomorphisms, right? At least under a certain group of diffeomorphisms, under infinitesimal diffeomorphisms, right? This transformation is generated by this vector here. And such that we have this transformation, okay? So if we plug this mu into our equations, the physics must be exactly, we will see that it becomes very more intuitive now in this expression here, right? If we see this h mu nu go into h mu nu plus some symmetrization of the derivative of the vector that generated the transformation, right? So they look very much alike here, right? So this is the analogy that we must make. So we made it. We wanted to build some kind of mathematical analogy with the gauge freedom of electromagnetism, and we did it. So we can calibrate this vector at our will, but it must always satisfy some conditions that we will get to. Okay.
Vitor,
But
there
we
is a
can calibrate
qualification
this
question.
vector. Okay.
So there's a quick qualification question in the chat. Someone is asking to confirm that H prime is evaluated at a different space-time point.
Okay, let me just, yes, H prime is being evaluated in a different point of the manifold. Yes, but these 2 points are connected through a diffeomorphism. So they are both, I think I can say this. These 2 points, the neighborhoods of these 2 points can be said to be isomorphic. Okay, so we have no quarrel here with this, but yes, H prime is being evaluated in a different point of the manifold. Infinitesimal distance, right? This is an infinitesimal transformation, right? It's an infinitesimal diffeomorphism. So is a point very much near x alpha, okay? But yes, very, very good point. Okay, so let's get back to our equations, our linearized equations, because now we have a very strong tool to help us simplify even more our equations, which are these transformations generated by a vector, which are the infinitesimal diffeomorphisms. Okay, let me just take a sip of water. So let's go. Perturbations in Minkowski space. All right. So No place, no good place to put this, but okay. All right, so the vector, this vector C allows us to get rid of unphysical degrees of freedom, right? If we have a gauge freedom, it means that our problem still has unphysical degrees of freedom, okay? By some time, we're gonna use all of our lifelines. So we're gonna use all the gauge freedom we have, and then and only then we're gonna be treating and dealing with only physical degrees of freedom. But we will get there. Okay. So the metric perturbation transformed as we saw here, right? So you could ask yourself, well, since our linearized Einstein equation here is in terms of the trace reversed metric perturbation, you could ask if how does the trace reversed perturbation transform, right? Under that diffeomorphism, under that infinitesimal diffeomorphism. So if we do this again, but now to the trace reversed, we'll see that the trace reversed perturbation transforms like this, okay? Now we're gonna use our freedom, right, here, right, with this expression. We can calibrate this vector such as to set this derivative equal to 0, okay? Such that the partial derivative of the trace reversed contracted with the partial derivative is equal to 0, okay? So this is what we call the Lorentz gauge, okay? The Lorentz is exactly the gauge that brings this derivative to 0, okay? So we calibrate this vector in such a way as when we take the derivative of the transformed, right, the h bar prime, we take the derivative and this derivative goes to 0, right? You take the partial derivative and the derivative goes to is taken to. In this gauge, we'll see that if we do that, right? If we calibrate this in just the right way, so this term here goes to 0, why? Right? Because it's exactly the same term. So the dummy indices here for you guys that haven't seen general relativity before, this being up and this being down, and here this being up and this being down, it makes exactly no difference at all. Okay, this could be down and this could be up. It makes no difference. In terms of the mathematics, this expression and this expression here are exactly the same. Okay. The important fact here is that this index here is contracted with this index here. Okay. All right, so this will go to 0. This will go to 0 also, right? And this term will go to 0 also. So we see we're gonna get rid of almost every term here, except for this one here. So this gauge simplifies a lot our expressions. So in this gauge, the linearized equation becomes this one here, right? So we took the Einstein tensor, the linearized Einstein tensor here. We put this equal to some eight pi t, right? Just like the Einstein equation. And throwing this 2, multiplying by 2 in both sides, and multiplying by -1 in both sides, we get this expression here, right? This expression here, for those who are familiar with electromagnetism, looks very much like what we get with the vector potential, right? Except instead of a 0,2 tensor here, we get a vector, right? Here. So this is always solvable by the method of Green's functions, because we know how to do this with this operator, right? And if we do look to this equation, we're going to focus now in the absence of sources, right? We're going to look to this equation far away from sources. So whatever generated this perturbation, this scenario that we're gonna look into now is very far away from this source. Okay, so we're gonna set this t mu nu here equal to 0, right? Such that we get this equation here, right? If we open up this operator, as we just to remind you guys what it means, let me see where I put this here, right? This is the partial derivative contracted with itself, right? Which we will call the D'Alembert operator, right? So if we look to this, the D'Alembert in flat space-time, right, is just like this. Okay, if we open up, this is a sum, right? In Einstein, in the Einstein convention, this is a sum over all the indices, and these indices, they go from 0 to 3, right? 0 representing the time component, right? 1, 2, 3 representing the spatial components, x, y, and z, right? But with the Minkowski metric, we will get that the first term, the 0, 0 term here, gets a minus sign, right? So we're gonna get a minus a second derivative with respect to time plus a second derivative with respect to the spatial direction. So we could represent this also by the Laplacian, right? So this would be minus the second derivative with respect to time plus the Laplacian, okay? In such a way that
Okay,
this
let me just
equation
interrupt
is
you for a
very...
sec. Take advantage
Okay.
that you returned to that slide. Someone is asking for a clarification of what you mean by an unphysical degree of freedom. I think you had this slide just there.
Oh, okay. Let me just find it. Okay. What I mean by these unphysical degrees of freedom, it means that it doesn't represent anything physical, right? It represents a mathematical degree of freedom, in the sense that it's just like when right here we got rid of let me just get back here with the coordinate transformations here. So you see that here we said that we got rid of 4 degrees of freedom when we did a coordinate transformation, right? We will see we saw yesterday in yesterday's lecture the Schwarzschild spacetime, right? And if we look, I'm going to give it an example because I think it's very much intuitive to see what I mean by an unphysical degree of freedom. If you can get rid of something in your expression due to a coordinate transformation, right? This is what I mean by unphysical degrees of freedom. So sometimes you can get rid of some things through a coordinate transformation, right? So it's like an unphysical singularity, right? What I mean by a physical and unphysical singularity, right? In the Schwarzschild metric, we had, I wish I had the Schwarzschild metric here, but I don't. Let me just pause here because this is important. Let me open the previous lecture if my computer allows me. Let me just stop sharing. Okay. Okay, let me just try to... Well, my computer is giving me a very hard time today. Very slow. But anyway, basically, what I mean by an unphysical degree of freedom is a degree of freedom in the equations that don't represent anything new, physically speaking. So when we solve for the perturbation, we're going to see that the gravitational waves, they have a given number of polarizations, right? But some of those polarizations are not physical in the sense that they don't represent different polarizations. They are the same polarizations as other polarizations inside the equation, but because of some symmetries and some coordinate system, because maybe we chose a wrong coordinate system, we are dealing with more degrees of freedom than we needed to, right? Because some of them we can remove through a coordinate transformation or a diffeomorphism. But I'm going to give you an example with the Schwarzschild metric. Just 1 second. Let me open the first lecture here. This is something that you would see, and maybe you saw when you dealt with black holes, right? If you studied black holes, you would have seen this. So let me just do this. Okay. I don't know if I So, okay, here we have yesterday's lecture, right? So let me take you guys all the way to the end where we saw the metrics, right? The famous metrics here, right? Schwarzschild spacetime, okay? So you see that if we analyze this element here is going to infinity, right? When R is going to 2m, right? So you would think that there's a singularity, a physical singularity in R equals 2m, right? But in fact, there is not. There is not. This happens here in this coordinate system because it is the wrong coordinate system to be looking at when we talk about singularities, at least real singularities, right? This is in a reference frame that does not help us at all when we're dealing with singularities and when we are dealing with the physics when you cross the event horizon, right? So what I mean by physical degrees of freedom is very much like this, right? So it doesn't represent anything true, anything physical. It's just a property of the coordinate system, the reference frame that we are looking into. Did this clarify your question? Okay, nice. Thank you, by the way, for the questions. They're very, as I said in the previous lecture, they enrich a lot the lectures. And okay, so let me get back to this. So here we have this expression, right? So we took the Lorentz gauge, we took the trace reversed perturbation and put it in calibrated the vector from our infinitesimal diffeomorphism in a way that we could make that this derivatives are equal to 0, right? In such a way that we simplified a lot our expression, right? In such a way that if we open up this operator here, we're going to see that this is exactly the wave equation, right? So here there is. So if you ever wondered where in Einstein's general relativity is the prediction of gravitational waves, here there are, okay? So what we did so far, let's get back and retrace our steps, right? What we did so far. we started with the assumption that our space-time is curved, but very little curved, not so much curved, right? In such a way that it can be modeled by the Minkowski metric plus a small perturbation, right? In such a way that we can view this space-time as a Minkowski space-time plus a where it lives some 0 to tensor field, right? So we have some 0 to tensor field propagating in a Minkowski background, okay? What we did later was to substitute this expression, right? Plug this expression into the definition of the Christoffel symbols, and we developed this expression always in first order in the perturbation, right? Because it is so small that terms of second order or higher can be neglected, okay? Then we plugged the expression of the perturbed, quote unquote, perturbed Christoffel symbols into the Riemann tensor, right? And we developed once again in first order in H, right? And we got this expression here. And then we took the contraction of the first and third indices of the Riemann tensor and got to the Ricci tensor, right? The perturbed Ricci tensor, in the sense that this is the expression we obtain, right? The Ricci tensor with respect to the metric perturbation, right? In the second derivatives of these metric perturbations, okay? And then we took the trace of the Ricci tensor such that we get the perturbed Ricci tensor, right? And we get this expression, and we put this all together to construct the Einstein tensor, which is exactly what is in the left side of the Einstein equations, right? In the right side of the Einstein equation, so we put an equal sign here, we have matter, right? We have 8 pi t mu nu, right? This is the left hand side of the Einstein equation, right? So now we have all the ingredients to construct the left hand side of the Einstein equation, which is the Ricci tensor, the Ricci scalar, and the metric, all in the perturbed regime. And we plug these definitions, these expressions here, and we got this very, very extensive expression here, right? So to help us, we introduced the trace reversed notation, right? This is not a coordinate transformation. Nothing is happening here other than a notation change, okay? So we call this the trace reverse perturbation, and we see how it behaves, and we see that it simplifies a lot. At least it looks a lot more friendly. Our expression looks a lot more friendly now, right? We have the linearized Einstein equation here. And then, well, we talked about how to get rid of some degrees of freedom, right? And we did it first with some properties intrinsic to the geometry here of the Einstein tensor and with the coordinate transformations. But then we saw that, in fact, in general relativity, coordinate transformations and diffeomorphisms are somehow equivalent, right? At least infinitesimal diffeomorphisms play a role very much like coordinate transformations in general relativity, right? In such a way that the invariance under coordinate transformations can be said to lead us to an invariance under infinitesimal diffeomorphisms, right? i.e. Transformations generated by an infinitesimal vector here, okay? In such a way that our physics is completely unchanged under this type of transformation, okay? So we transformed our perturbation to a perturbation that will alter our original by some vector and its derivative, okay? So that we can calibrate this vector in such a way as to obtain results that we want, that will simplify our problem, okay? And it's just what we did, right? We transformed, we saw how to transform the trace reversed under this infinitesimal diffeomorphism, right? And we and we invoked what we call the Lorentz gauge, right? To see what this guy would look like, so this could be possible, you have to plug this here, take the derivative, and set the derivative of the transformed h mu nu bar prime equal to 0, right? So we take the derivative on this side, take the derivative on this side, and you're going to have a differential equation that this vector must solve, right? A second order differential equation that this vector must solve. So this could be possible, right? We're not going to get into what differential equation is and how to solve it, but we can always solve this because, as you can imagine, to take this derivative here and contract with this index here, we see that we're gonna have a del mu here contracted with a del mu here, which means that we're gonna have here the D'Alembert operator, right? Which is always solvable, right? At least through the method of Green's functions, we can always find a vector that solves the equation in such a way as to make this, the derivative of this perturbation equal to 0. Okay. For more proof on this, you can always check the references. Some of them do this proof, some of them don't, right? Some of them get to the differential equation and only use the fact that due to the operators on the left-hand side and the method of Green's functions, we can always solve them. So we don't have to worry at all if we can do this because we always can, okay? And then we use the Lorentz gauge to simplify furthermore our expression, okay? And then we got the much more simplified linearized Einstein equation in the presence of the source that generated such perturbation, right? And then we saw that this can always be solved by the method of Green's functions, but it could be even more easily solved if we look at it far away from sources, right? So let's see how this perturbation looks like far away from sources. And you can see very intuitively that this is the wave equation, right? So now we just proved to you guys that in the linear regime, the Einstein theory of general relativity predicts the existence of gravitational waves, right? So the metric perturbation implies gravitational waves. Are you excited? I was when I first saw this, but I mean, to each his own, right? So let's go further because we're gonna see how this kind of gravitational waves look like. And then we're gonna start with an ansatz. So we have a differential equation, and what we physicists do is, well, I think by the look of it, that this equation could be solved by this. Okay, so we use this ansatz where P mu nu bar is the polarization tensor, just like we use the polarization vector in electromagnetism. Here we're going to use the polarization tensor, and K is a wave vector. Okay, it's the wave vector. This object here, if you open this in the Einstein summation, you would see that this is exactly correspondent to a wave traveling in some direction that we didn't stipulate it yet, but you would obtain k t right here, 0, 0, right? In fact, k is a vector with components omega and k vector, right? So the first term in the summation here would be omega t minus k vector k x vector, right? In the inner product. But well, if we put this into our equations, so if we plug this in here, right, and and do the derivatives, the subsequent derivatives, right? We get this, that this equation implies this, this expression here, right? I didn't talk to you about yesterday about the types of vectors in our spacetime, right? I didn't talk to you about what it means for a vector to be a time-like vector, or a space-like vector, or light-like or null vector, right? But basically, the inner product of some vector with itself, right? The norm, as we would say, the signal, more accurately speaking, will tell us the character of such a vector, right? So if we took, so you see that this is exactly what we are doing here. We're taking the inner product of K with itself here, right? We are contracting a vector with itself. So I take the inner product of this vector with itself. If this inner product was negative with the signature, metric signature that we are using, if this was negative, this would mean that this vector would be a time-like vector. What this means that this vector is tangent to a time-like curve, which is exactly what represents the path of massive particles in our space-time, okay? Particles that travel at speeds less than that of light, okay? If this inner product was positive, right, it means that this vector is tangent to a space-like curve, which represents the path that objects traveling above the speed of light take in our space-time, which means nothing, right? In this theory, nothing travels faster than light, right? So space-like trajectories are not taken by any particular particle or any object in our space-time that is of relevance, okay? And then we have the case that we have here. So if this inner product is equal to 0, it means that this vector is tangent, which is the path of light rays, right? Of photons in our spacetime. So what it means that the wave equation, when we plug this in the wave equation, right? If we take these ansatz of the metric perturbation and we plug this here, we obtain that the wave equation implies that the wave vector is a null vector, which means basically that this wave is traveling at the speed of light, okay? So this is huge because we now know that gravitational waves not only are predicted by the Einstein equations in the linear regime, but they also travel in the speed of light, okay? Some would say, right, with the interpretation that we provided in the beginning of this lecture, that this could be said to be a 0 to tensor propagating in Minkowski spacetime. So so perturbations in Minkowski can be seen as a massless spin-2 field traveling in a flat space-time, right? This spin-2 field is exactly the gravitational wave. So gravitational waves can be seen as massless spin-2 fields propagating in a flat background, okay? So we have this very important result that gravitational waves move at the speed of light, all right? As Wald states, gravitational waves may be seen as massless spin-2 fields propagating in flat background. Massless, right? Because they're traveling at the speed of light, okay? And spin-2, because, well, we have a rank 2 tensor here, right? So in this sense, we can see the gravitational waves as massless spin-2 fields propagating in a flat background, at least in this context, okay? So let's see what the, well, okay, so we plugged the ansatz into the wave equation and we obtained this, right? What happens if we plug this into the Lorentz gauge expression, right? Because the derivative, the partial derivative of this contracted with this first index must be equal to 0. So let's see what the condition of the Lorentz gauge implies. So it implies this expression here, which basically means that the direction of propagation are always orthogonal to the polarizations, right? The polarizations must always be orthogonal to the direction of propagation, right? Which is the same result we obtain with electromagnetic waves, right? So here, gravitational waves will only have transverse. It's the same result as we obtained in electromagnetism. Okay, but this ansatz here, we are dealing with a single plane wave, right? So a more complete solution would be a superposition of plane waves, right? Where here we take the real part because we see that this object here, well, it could provide us with some imaginary, right, components with imaginary elements, but our gravitational wave is a real object. So we have to take care, we make sure that we are taking only the real part of this. Of course, that in a superposition of complex objects, you can always do this combination in a way that we end up with only the real part, right? But just to make sure, this is the true and complete expression for the solutions, right? And here we see what happens when we open this object here. When we open this up, we get exactly this, which, right? We get the frequency omega t plus ki xi here, which are the spatial components of the wave vector, right? And where we did just this, okay? This component is equal to 0 here because we had to lower the index. To do that, we applied the Minkowski metric, right? So in doing so, the Minkowski metric always changes the signal of the first component in this, at least in this signature that we are using, in this metric signature, okay? All right, so the thing is, we still have some gauge freedom, right? Because the condition that we imposed on the vector that generated the infinitesimal diffeomorphism is not completely determined by that condition. And that condition was the fact that this vector must have a particular form such that when we take the derivative contracted with the first index here, the derivative of this new perturbed tensor must be equal to 0, okay? But this not completely defines who is the vector, this vector, okay? So we have still some liberty to take, that we are allowed to take with this vector, right? It doesn't completely defines him. So we're gonna use this in our favor, right? So we're gonna make a subsequent infinitesimal transformation, again by the same vector, right? So we transformed our tensor once, and we do it once again because, well, if you forget the first reference frame, the PGC, right, the principle of general covariance, demands that this reference, that the physics in this reference frame is the same in this reference frame, right? The same way that this reference, the physics in this reference frame must be the same physics in this than this that in this reference frame, right? So in doing so, the subsequent gauge condition, what happens is that if you do the calculations, if you plug in this condition, if you do this once more, right, and open these equations and see what this implies for the vector, you will see that this demands that this condition, right, so that you do a subsequent transformation, and we still have the same physics, the same perturbation, in such a way that it preserves the Lorentz gauge in this reference frame. The vector must obey this differential equation here, right? Which we can always solve because, well, this operator is always solved by the by the method of Green's functions, right? So we see that now we have totally defined this vector, right? Because now we have a expression for this vector alone. Before we had an expression for this object here, right, in terms of the metric, of the flat metric, and so on. Now we have an expression for the vector itself, right? So now we used up our leftover gauge freedom, and now we got rid of all the degrees of freedom that we could, right? And now what is going to be left is only physical degrees of freedom, right? But we're going to see that once more. So calibrating this vector, we are able to set this component equal to 0 and the trace equal to 0, right? This is another gauge freedom. This is another gauge that we call the transverse and traceless gauge, right? Transverse because this component goes to 0, and traceless because the trace goes to 0 also as well, okay? I know that it looks like we are cheating, right? But because I'm not really showing the mathematics behind this, but it would take us a very long time to do so. So we're not doing this. But okay. So we use this gauge in our favor. So we calibrate this just so that we can do this, so that we can do this, right? So right away, if the trace is equal to 0, so it means that the trace reversed perturbation is equal to h, right? Because the relation between this perturbation and this was him minus a half the metric times the trace. So if the trace is 0, these two perturbations are equivalent, right? The notations are completely equivalent. And opening the Lorentz gauge expression, we see that we get these two expressions here, okay? So we have this expression here and this expression here, right? In the Lorentz gauge. Let me get back to the Lorentz gauge so that you are not confused. This is the Lorentz gauge condition, right? So here is a sum for each value of this index here. You have an equation, right, with the sum. And you have, in fact, 4 equations here, right? You have an equation for nu equal to 0, an equation for nu equals to 1, 2, and 3, right? So open this up, we take for nu equal to 0, we have this equation, and here we have the set of 3 equations for each value of j, right? And we see that due to the transverse and traceless gauge, this guy will go to 0, right? Because this gauge implies that age 0i is equal to 0, and since this metric is a symmetric tensor, so age I 0 is also equal to 0, right? So this guy will be thrown out. This element will also, this object will also be thrown out, right? And then we see that due to the trace being 0, we can always make, I'm sorry. we can always make this derivative equal to 0, right? Why? We're going to see that this derivative, the derivative of age 0, 0 is equal to 0 due to this being equal to 0, and this will be equal to 0 due to this being equal to 0, okay? And we have these two constraints, okay? We are able to set age 0, 0 equal to 0 because we are talking about a static metric, right? A metric that is completely time independent, right? And the time dependent part of the gravitational wave is what matters, right? If in the Newtonian limit, so if we did the perturbation from the beginning of the lecture, right there when we started from the metric, from the Minkowski metric, and we modeled our perturbation as the Minkowski metric plus some small perturbation, if we added to the condition of the weak field, the condition that things are moving really slowly, right? We would obtain the Newtonian limit. And in this limit, you can show that this component of the perturbation is equivalent. It is related to the Newtonian potential. Okay, this can be seen in Carroll. You can see this in a way to prove that general relativity regresses to Newtonian gravity when we take the limit of weak gravitational fields and bodies moving very slowly. Okay, so we can set this equal to 0 because it is completely irrelevant to in the context of gravitational waves, which which are about the time-dependent part, right? The part that oscillates and so on. Okay, so far away from sources, since this guy is related to 2m over r, if you're not convinced with this argument, you can always say, well, okay, far away from the source, this r goes to infinity, so this guy, I can set this guy equal to 0, okay? So in such a way that the TT gauge, but what I mean by TT gauge, I mean the transverse and traceless gauge, right? It means that this trace demands this. It implies this, okay? So age, the trace is equal to 0, right? These components are equal to 0, right? And the derivative and the spatial derivatives of these components are equal to 0, right? So now we use our invariance under coordinate transformations. We use the Lorentz gauge. We use the TT gauge. And now we are all used up of all our gauge freedom, okay? So now this means that there are not unphysical degrees of freedom for us to get rid of, okay? So what is left is completely physical and real, okay? And are things that we cannot throw out. So if we get back to the solution, right? Here I forgot to take the real part of this, but never forget that we are always taking the real part of this superposition, okay? So note that the gauges, they impose restrictions on the polarization tensor, right? By imposing constraints on the perturbation, it indirectly imposes constraints on the polarization tensor, right? And we will see what they are. So the Lorentz gauge implies this, right? Which we already discussed, which means that there are only the only polarizations that are allowed here are transverse polarizations, right? Those that are transverse with respect to the direction of propagation of the wave, okay? We also see that by the Lorentz gauge, we also see that since that this will be the trace of the polarization tensor will be equal to 0, right? And due to the TT gauge, right, due to this being equal to 0, it means that these components of the polarization tensor will also be equal to 0, okay? All right, so now that we have our constraints, let's see with an example, right? So let's imagine that our wave propagates in the x direction in such a way that we can write our wave vector in this form. How you may wonder how I constructed this vector. I constructed this vector reminding myself that this vector is a null vector. So the inner product, its inner product with itself must be equal to 0. So I constructed this in such a way that I know the first component must be equal to omega, but by definition, but the second component it must be also equal to omega in such a way that when I lower the index, I obtain this vector in such a way that when I take the inner product, this inner product is equal to 0, okay? So this vector is constructed in this way to preserve the fact that this vector must be a null vector, right? Okay, so now we have a wave propagating in the x direction. So the polarizations must be in the YZ plane, right? So if we do this, so if we apply the condition that only transverse polarizations are allowed, and given the fact that these components are equal to 0, we have this, we translated this expression into this matrix multiplication here, right? Which gives us the fact that these components must be equal to 0, right? If you take this matrix multiplication here, we will see that this produces this, okay? Thus, what we have left are these 2, right, degrees of freedom, because since the polarization tensor is symmetric, so the component P23 must be equal to the component P32. So here, this component, we called it P23. It is actually the P32 component must be equal to this. We labeled the same way, okay? And we labeled this, which we called first P33, right? But we labeled it minus P22 because the trace of this matrix must be equal to 0, right? And the only way is to sum this component with this component and set it equal to 0. And the only way to do so is by P33 being equal to minus P22, okay? So now we have the polarization tensor, the physical polarization tensor with the physical degrees of freedom. If we haven't used our gauge invariance, our gauge freedom, all the gauge freedom that we had, we would have other elements here present, right? And they would mean nothing because we could easily set them to 0, equal to 0, using some gauge freedom, using some gauge transformation. Okay, so that is what I meant by a freedom. Now, all this degrees of freedom here represent something, physically speaking, right? And we're gonna see now what they do represent physically. So we're gonna relabel P22 and P23 by P plus A. Well, I used the wrong notation here. It's not a PX. It should be a P cross. So like a times symbol, right? Like a cross product, right? You should be cross here, not X. I'm sorry for this. I'm gonna correct this before I send it to you guys later today. So okay, so here we don't have the correct one. I'm so sorry. But okay, but this we'll call P plus and P cross, okay? And we'll see why we labeled. So now we have our I'm sorry, our tensor, our polarization tensor. And you see that we took the matrix that inside the matrix, right? So we excluded the time components of this matrix, and we focused on this 3x3 matrix here, right? Which is this matrix here. It is exactly analogous. You only add a row and a column, and a row and 3 columns here of zeros here, and so we have the same matrix, okay? So plugging this matrix back in the equation for the metric perturbations and taking the real part of this exponential, right? The solution for each frequency, right? For each plane wave of frequency omega, remember that the real complete solution is a is a superposition of plane waves, each with a given frequency omega, but we're looking at the solution for each one. So take one of these plane waves of the superposition and see what the solution looks like for each frequency. And this is the solution, right? So this is the polarization tensor. If we open this up using the fact that that the wave vector now is on the direction of on the x direction, right? So this inner product here yields this this argument for the cosine here. It could easily be a sine here or a cosine here. The difference is only a phase, right? So physically, we're talking about the same result here, okay? So for the details and the formal analysis of the effects of the gravitational waves on particles, you can see the reference by Maggiore, which does this with very, 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 very much detail, okay? Because this is what we're gonna see next, okay? We're gonna talk about now what happens to matter, to a group of particles as a gravitational wave is passing by, okay? I'm not gonna do this here in the most rigorous way because it involves introducing concepts of geodesic deviation and other concepts that would take a long time to do. So if you want a more formal approach, you can always see the chapter by Maggiore, Gravitational Waves Volume 1, which is in the reference here. You can always check that for the formal analysis. But to give you guys the intuition on how what the perturbation does to the perturbation does to matter, right? To the matter configuration, we will look into now with some intuition. Let's see. Okay, so let's get back to the Minkowski metric, right? Remember that the metric G mu nu, it gives us a notion, an invariant notion of how to calculate distances in our space-time, which is the line element, right? This line element here, the s squared, is completely invariant under coordinate transformations, right? And in the Cartesian coordinates, the Minkowski metric, it looks like this, okay? As I stated earlier, remember that I said to you guys earlier, because this metric was in spherical coordinates in the slides of the previous lecture. But here they are in Cartesian coordinates, and it is easy to see why the derivatives of the Minkowski metric, Minkowski metric components are equal to 0, because right, you have -1 here, 1 here, +1 here, +1 here. So they're all constant, so the derivatives go to 0, right? Which means that you plug the derivatives of the metric into the Christoffel symbols. It would mean that the Christoffel symbols are equal to 0 in this coordinate system, which would mean that in this coordinate system, the Riemann tensor would be equal to 0 also, and so on and so forth, right? It would be easy to see that this represents, in fact, a flat space-time, all right? Okay. And just to be sure, even though the Christoffel symbols may not be all equal to 0 in some other coordinate, in some other set of coordinates, but the curvature tensors will be, okay? In some sort of combination in the nonlinear way, they combine the derivatives, they will be equal to 0. The components will be equal to 0. Okay. You can try this by taking the metric in spherical coordinates, computing the Christoffel symbols, and trying to compute the Riemann or Ricci tensor components, and you will see that even though we are not in Cartesian coordinates, this still represents a flat space-time. Okay. So if we turn the perturbation on, so this is the Minkowski metric with the perturbation turned off. Okay. So here all we have, so if we take this equal to 0, g mu nu equal to eta mu nu leads to this line element. Okay. Now if we turn this on, we turn we turn the perturbation on, the switch, we flip the switch and we turn this on. What happens to the line element? It becomes like this. Okay. It becomes exactly like this, right? How can you see that? How you went from this to this? Well, components, right? Because in here we have the components of the metric perturbation, right? So you see that we have no perturbation because we set age 0, 0 equal to 0. So the time component will not be perturbed, right? So G00 is exactly N00, which is -1 in these coordinates, okay? Because age 00 is equal to 0, right? But age 11 and age 22 and age 33 are not equal to 0, right? Because age ij are not all equal to 0 always, right? It has a time dependence here, right? So we will be 0 sometimes, but sometimes it will not, okay? So if we substitute, right, these components, remember that the line element is defined by g mu nu contracted with dx mu dx nu, right? So if we open up the sum, we get this new line element if we turn the perturbation on, okay? So you will see that if here we took the age 2, right? What is the H22 component? If we look back here, H22, we need the P22 here, which is exactly P plus, right? Times the cosine, right? It is exactly what happened here, right? What is adding to the 1 from the Minkowski metric is exactly P plus times the cosine here, right? The same will happen with Z, because Z in the Z direction, in the Z coordinates, so we need age 33, right? If we go back, age 33 implies we use the P33. P33 is exactly minus P plus, right? So P22 is plus P plus, and P33 is minus. So this leads to here, this this delta, right? This extra term is adding to the Minkowski term, and this is and this same term is being subtracted here, right? And then when you take the cross terms, so age 1, age 1, 2, age 1, 3, and so on and so forth, we're gonna have this element, this delta here, which is the cross. Now here we have the right right notation. This is the that I intended to use here in the P cross. It became PX. But I'm gonna correct this before I send to you guys. I'm quite finishing, so bear with me. We're quite getting to the interesting result. So you see that the line element is altered, which means that the notion of distances in our space-time are changed by the passing of this gravitational wave, right, through our reference frame. So we have a reference frame, this coordinate, this metric perturbation passes through our reference, the origin of our reference, and it causes to shift in some sense our notions of distances in the y direction, in the z direction, right? And also in the directions that are 45 degrees with respect to y and z here. We're gonna see that, okay? We're gonna see that these two polarizations, right, is what we call the plus and cross polarizations, right? You're gonna see why we call these polarizations plus and cross. But as I said, the gravitational wave passes by, and distances between points in our space-time are changed, all right? In particular directions, right? Only in directions transverse to the propagation, because the polarization of the wave are always transverse, okay? So imagine that we have a system of particles in the YZ plane arranged in a circle, right? And this circle is centered at x equal to pi over 2 omega, right? So the point, we are fixing a plane, right? We're taking the YZ plane is in that cross x in this point here, in the value of x, pi over 2 omega. If we do this, we transform this cosine to a sine, right? Because it's easy to see. Okay, you could choose another value for x, right? It would be exactly the same physics, okay? It's just to simplify our equations, okay? So as time progresses and the gravitational wave pass through x, through this plane, what happens is this. So at time equals 0, the shifts that the perturbation causes is equal to 0, right? Because at time equals 0, the gravitational wave didn't pass through yet, right? So we have the particles arranged in the same way that they are in the beginning, okay? So a little time before that, as the gravitational wave passes, we have some shift, a positive shift here, right? And then sometime later, it goes back to 0, right? And then we have a negative shift, okay? So to see what this looks like, so we have here exactly the system that we're talking about, okay? So now we have these are particles in a circle, time t equals 0, and then as the gravitational wave passes through, the notion of distances between our particles change. You see, the particles did not, I mean, what is actually happening here is the concept of geodesic deviation is changing, right? The notion of the distance between these two particles here changed, right? The geometry changed. okay? So you see that this particle is unchanged, the position is unchanged, this position is unchanged, and also, but remember, what changed here was not the position itself, but the notion of the distance between those particles, okay? So if we do this sometime later, the configuration goes back as it were before, right? But then sometime later we had a negative, right? A negative shift. But since in the y we are summing the shift, the negative shift really it seems to diminish, right? To decrease the distance between these two particles, and increase here because we were subtracting in the z direction, and since the shift is negative, then we increase the distance between them, okay? The same, so this is what happens if we have strictly the plus polarization, which means that this polarization here is set equal to 0, and we only have this shift happening, right? So this would be equal to 0. So we have the plus polarization, and you see why we call it plus, because it shifts and it oscillates between this four configurations, right? This is why we call it a plus configuration. In the cross polarization, which means to set this shift equal to 0, and this would be the only shift present, the same thing happens, but the axis in which it occurs, the shift in which the alteration occurs, is rotated at 45 degrees, okay? And you could ask me, well, okay, but what happens if we leave the 2 on? We set both different to 0. Well, then you're going to have a combination of these two polarizations here. And if you set the amplitudes of these polarizations exactly the same way, you can produce a circular polarization here, okay? I didn't bring this today, but I can bring it tomorrow, because we already did our time here, but I can show you tomorrow that, well, that this can happen, and we can see videos and animations to see this happening, right? These oscillations happening, which are pretty cool, and I can show you tomorrow for you guys, because if I try to do this now, my computer will call it quits. So this is what happens when a gravitational wave passes by. When it passes by, after it passes by, this configuration is back to its original configuration, right? Because there is no more perturbation. This perturbation is time dependent, and as the gravitational wave passes through, the perturbation ceases eventually. And that's it. That's it for today. Well, today we saw a little bit of how does the Einstein equations predict the existence of gravitational waves, right? And we saw the effect of these gravitational waves as they travel in a flat space-time, okay? And tomorrow also I can discuss, if you want, maybe not tomorrow, maybe in the last lecture, you can discuss how we detect in a very intuitive way, because the detection of gravitational waves is very complicated, right? You have to take into account the reference frame of the detector in comparison with the reference frame of the wave that is propagating. So there's all these things that have to take into account, but we can do some intuition, as we did with the effects on a set of particles, a configuration of particles here, so you guys can see how we detect these shifts, because these shifts of this shift of the notion of distances in our space-time is what we detect with the with the LIGO interferometer. Okay, so tomorrow we start perturbations in curved space-time. Okay, which is a little bit more complicated to do. We will need to use spherical tensor harmonics and things of this sort, but we see that later tomorrow. So I thank you all again. Thank you, Bruno, for the assistance, and I see you guys tomorrow.
Well, thank you, Victor. I think we do have a couple of quick questions in the chat. So if you have time just to quickly,
Okay.
yeah. So let me just summarize them. The first is concerned, well, they saw the derivation of the propagation of gravitational waves on a flat background, and they wonder if there are gravitational waves in the curved backgrounds as well. So maybe you can comment just a few words on that.
Okay, let me just can you repeat the question?
The question
Please?
is, are there gravitational waves in curved backgrounds, or is it a peculiarity of flat space?
No, 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 no. We're gonna see tomorrow, we're gonna start to see what happens when we apply this same reasoning. So we're gonna start with a curved background, which is the Schwarzschild background, which is the solution for the geometry outside a spherically symmetric object, okay, which can be a black hole, okay. It can represent a black hole. So we're gonna see what happens in flat backgrounds. So for certain, gravitational waves are not a specific property of flat spacetimes, such that our spacetime is highly not flat, okay? He's locally flat, but he's not flat, and we detect those gravitational waves. So they are propagating through a curved spacetime, which is the real spacetime in which we live in. So yeah, so there's this. I see a question: if gravitational waves are predicted for small perturbations to flat spacetime, do not predict their existence near their own source. Okay, yes, the source distorts the spacetime also, but we are considering a source that has that curves the spacetime around it in an amount very much smaller than the solution. So I mean, for example, tomorrow we're gonna see Schwarzschild, right? So we could take a black hole, for instance, a spherically symmetric black hole, and we could take some object that will perturb the geometry of this Schwarzschild black hole. Okay, so this perturbation could be any sort of things, any type of perturbation that is massive enough to perturb it, but small enough as to the curvature around the perturbing object is not comparable to the curvature of the object, right? Of the object that is curving the space-time background, the background space-time. Okay, so there is the question of how to see this interaction of the gravitational wave and the curvature of the source, but it is something that we are not considering here. Okay, we are disregarding the effects of the curvature around the object that is causing the perturbation. Okay, this is something that is important when people try to study the gravitational waves produced by a binary system, for instance, because we're talking about two very massive objects orbiting one another, two black holes, two neutron stars, and so on. And to do that, we need numerical relativity, right? To do that, we don't have analytical methods to do so. So in that regime, we cannot disregard the around the object that is causing the perturbation, right? Because the two objects orbiting each other and causing these gravitational perturbations are very massive. So is that what they call this very strong gravitational regime, right? So I think I don't know if this answers your question. And let me see what else we have here. Do we have gravity waves get damped as they travel through space-time? Yes. Yes, they do get damped. They do get damped. In fact, one character of gravitational waves that are very useful to understand, to get information from gravitational waves, one characteristic that we take from them are the quasi-normal modes. Okay, we study quasi-normal modes of gravitational waves because they help us understand the sources, right? The sources that generated those gravitational waves. And as you can imagine, these quasi-normal modes are the modes that survive after all the other modes they die out. They start to die out. The quasi-normal modes are the predominant ones, and eventually they are going to fade away as well, right? So yeah, the gravitational waves get damped as they travel through space-time. Yes, I can show you, maybe if you have time in the last lecture, if there is some time left, we can talk a little bit, and at least show you how these quasi-normal modes look like, right? Basically, we take the solutions of the Reggie-Wheeler equation, which dictate which are the master equations governing perturbations, which are a Schrodinger-like equation. And we take the solutions of these equations, and we take the limit for our coordinate going to infinity. So we look at this very, very, very far from the source, right? In such a way that the unstable modes are going to fade away, are going to die out, and the normal modes are the last ones that survive. Okay, so yes, there is a damping of the gravitational waves. Okay, do gravitational waves scatter near massive objects? Yes, yes, yeah. Everything that you may wonder that happens. I don't know if everything is the right word. Perhaps a very strong word, but I think that pretty much everything that happens, because as you see, as Walt says, gravitational waves can be seen as massless spin-2 fields propagating in a flat background. So I think these questions are coming up because you are doing the right association, right? You are asking yourselves and wondering why, if the same phenomenon with electromagnetic waves also happen with gravitational waves, and the answer is yes. There is a difference, right? Because we are talking about spin-2 massless, but spin-2 field here, right? Which is different from the electromagnetic wave, which is represented by spin-1, if I'm not mistaken. Field, massless field, propagating in flat background. But so there is some differences, right? This field interacting, the gravitational waves interact with itself, all that things that people from particle physics know a lot more about from studying gravitons than I do. But yes, gravitational waves scatter, and exactly the study of quasi-normal modes involves bringing gravitational waves to the study of scattering, to do scattering in gravitational waves in some way, right? So we talk about a potential, and how the gravitational waves scatter in this potential, and so on and so forth. So yes, they do scatter. Let me see if there is another, okay. If GW propagates in X direction, the change of the distances occurs in the Y and Z directions. Yes. Yes. So as we demonstrated, yes, I think I answered right after the question was asked. But yes, so if and if you can imagine, if the gravitational wave propagates in the Z direction, the notion of distances in the X and Y directions will be changed, right? And the same if it is traveling in the Y direction, the notion of distances will be shifted in the Y, in the X and Z directions. Okay. So anything else? Any questions left? I have time. You guys be free to ask anything you want. Well, so I guess that's it. So I'll see you guys tomorrow. Tomorrow we start to answer a little bit more properly some of these questions when we see how these gravitational waves behave in the short shoot, in the curved background of short shoot space-time. So thank you, Bruno, mais uma vez, once
Thank you.
again.
Yeah, thank you everyone for coming, and thank you, Vitor, for the lecture. See you all tomorrow.
See you.